Alrighty. Okay. Um, what do we have today? Number of ways to arrive at destination. You're in a city that consists of n intersections numbered 0 to n minus 1. Okay. Very similar to the last couple of problems. I think it's going to be another graph with bidirectional roads. Pretty much an undirected graph between some intersections. The inputs are generated such that you can reach any intersection from any other intersection. Okay. So the nodes are like the intersections and the edges are the roads. Okay. And that there is at most one road between any two intersections. Okay, so there's no like cycles between two things. You can cycles of two roads between two nodes. You're given an integer n and a 2D array of roads. Where roads of I is uv in time, so it's kind of like a weight between two nodes, time being the cost or the weight of the edge. Means that there's a road between intersections u and v, that takes time. Okay. You want to know in how many ways you can travel from intersection 0 to n minus 1 in the shortest amount of time. How many ways? Return the number of ways you can arrive at your destination in the shortest amount of time. Since the answer may be large, return it modulo 10 to the 9th 7. Okay, so it's pretty complicated here. Determine the number of ways you can arrive at your destination. Okay, your destination being n minus 1. Oh yeah, okay, so you start at 0 and you end at n minus 1. The shortest amount of time it takes to go from 0 to 6 is 7 minutes. And there's 1, 2, 7, the 5, 2 is the second way. 2, 3, 3 is too long. 2, 3, 5, 2, 3, 1, 1 is also 7 minutes. And then 2, 3, 1, 1. So there's 4 ways. Okay. And then here, there's the road here is just from 0 to 1, and there's 2 nodes, so it takes 10 minutes. The shortest amount of time is 10 minutes, and the number of ways to get there is 1. Okay. Alright. I think this is going to be so the graph, yeah, okay, let's just go ahead and make a graph 2D array here to map the exit nodes from some start node. And I guess this graph should also take into account the weight, which is going to be a tuple. So we can make a 2D array for this. Generally, it could be a hash map using a default dictionary of lists. Can make graph using default dictionary of lists of tuples, or just a 2D array, which is going to have a list of tuples. 2D array where rows list of tuples. Alright, since I think it's going to be slightly faster if you use a 2D array when you have numbered indices like this rather than string indices or something like that, we should use that. So we'll say our graph is equal to an array of lists, 2D array of lists, and it's going to be size n, and for each edge in the graph, or in this case road, for each road in roads, we'll say UV and time is equal to this road, and we'll say the graph at U appends the tuple that is V in time. Similarly, since it's bidirectional, the graph at B appends the tuple that is U in time. And just to make sure that this is working correctly, I'll just print the graph and verify. Index out of bounds. Interesting. Which index is out of bounds at this moment? 0.6. Oh, I keep on forgetting the syntax. It's supposed to be for k in range n. Can't actually do multiplication on this. Alright, so here's our 2D array. So the first row is that. So from node 0, it connects to node 6 with weight 7, time 7 minutes, or 7 whatever. Connects with node 1 at 2 minutes, node 4 at 5 minutes. And this is our second row. From node 1 connects with node 0 at 2 minutes, node 2 at 3 minutes, and node 3 at 2 minutes. Okay, so I think this is all correct. Now, so we want to find the shortest amount of time from 0 to n minus 1. There might be a lot of ways, so we'll say we'll have a mod constant, which is 10 to the 9th plus 7. Answer is going to be equal to 0. Alright, so I think what can happen here is I think we need to use a heap so there's unlike graphs that are unweighted, where the depth of the search for a path between two nodes is kind of based on how many nodes are between them, right? So like if the graph is unweighted, if the graph is unweighted, it's kind of like having a weight of 1 for all the edges. And when you do a breadth first search, where you search every kind of adjacent node to a starting node, and then the second level to that, and the third level to that, to figure out like the shortest path. Here, you don't know what there could be a very long connection between the start node to the next node, where there were where the cost of that, the time cost of that, could have been shortened using a kind of more numerous node path, where the costs of those more numerous nodes are like smaller in sum than the overall big cost. So in any case, the way that we should probably approach this is using a heap, where a heap is a data structure instead of using a stack or double-ended queue to stored slash traverse traverse graph. Since the cost makes it so that a longer path and having more nodes might have lower cost traverse by the current lowest cost options. And a heap is something where heap is a data structure where you can always get the lowest value from the heap, which in many ways acts as a otherwise acts like a stack or an array in terms of like you can get the first element, you can append to you can add stuff to the heap. So yeah, so I don't know if I have done heaps as daily yet, not that I recall. Or a daily that I've recorded. So we'll start with a heap and we can just get an array for that. And so we first need to determine this is interesting. Okay, so there's two components here. There's an answer time and answer frequency. So there's a lowest amount of time to reach the end node, and I guess this should probably start with something huge. And there's a frequency with which that time is encountered. So we'll say that's 0. Yeah. So what we can do is we can start the heap with just the first node and the cost of that node. So here we'll say 0 and 0, and the heap has tuples of node and cost to node from start. And since is it possible to go in loops? Yeah, it's possible to go in loops. So how do you prevent going in loops here? So you go here, I guess because the costs are always increasing, as long as you have a lower cost to get to that next node, then you should go there. I think we also need another track, and that's going to be the lowest cost to get to a particular node. The lowest cost to get to a particular node. I wonder. I think maybe the answer time and answer frequency might be already stored in there. Okay, so I think here we need a low time array. Yeah, low time array, and it's going to be starting with the biggest number possible. Times n and a and low frequency. So I think instead of just considering that I need to track how many times, the lowest time to get to the end node and how frequently that is, I need to keep track of actually for every node what was the shortest time to get to that node and how many ways to get to that node, because that will be part of the calculation to get to like the end node. So I don't think I actually need this. This is just going to be the last the last values in these two arrays. So I'll say I think I need a current heap. Yeah, I just need the current heap should be 0, 0. Yeah. Okay. So while there is something in the heap, while heap has something, is it possible that there's no path? There's always a path, right? Okay. So we'll take the top node and cost from the, I guess in the syntax of this thing, it's going to be intersection and intersection. I'm just going to call it nodes. The nodes are the intersections. Node and cost from the heap. And when you pull stuff from the heap, you have to use heap q dot heap pop. And then the heap name. Actually, that's I think that's the syntax, anyways. And then here we're going to see if this cost is less than the current time recorded to get here. So if the cost is less than the load time for this node, then, or let's say if it's bigger, then we just ignore it, right? Greater than the load time for this node, then continue. If the cost is equal to the load time for this node, then this is just going to be another way to get here, but we don't really want to pursue that further. So the node frequency for this cost is, the low frequency for this node is going to be incremented, and we also continue. All right, so here do stuff for finding a new best path here. So at this point, the way that we've gotten to this node is optimal, and we want to explore. So we're going to set the low frequency for this node, or we'll set the low cost for this node to be this current cost. The low frequency for this node to be reset to 1. Load times array name. And then for each neighbor of this node, for each neighbor in the graph of this node, where there's going to be a neighbor and the neighbor cost to it. Do I need, how do I prevent cycles. Prevent cycles now or later? I feel like I should probably prevent cycles now as well. So there might be a double check. So if the neighbor cost plus the current cost is less than the graph, the low cost, less than or equal to the low cost for this neighbor, then we're going to append this to the, or not append this, but we're going to add this to the heap. So heap q.heap push onto heap the tuple that is this neighbor and this neighbor cost plus cost. And otherwise we ignore this. Not quite right, because that's not quite right, because this doesn't increase the frequency at which something occurs. This doesn't increase the frequency with which something occurs. So I think I need to include the so the first time you detect that there is a quick way of getting there. So let's say you found that from 0 to 6 the lowest cost was 7. But let's say, how do you, so the issue that I'm trying to think through is if you have a lowest cost between two nodes, and then you later on find that there is another way to get to that node with low cost. So let's say there was like 0 to A and A to 1, where that extra path added to the frequency. How do you push that information down to the way that you traversed all the way to the end? So because then it increased the overall cost. So I think maybe is it possible when you update a path, no, when you use the heap, can you include the number of ways to get to this node? Not really, right? So you include the number of ways to get to this node within the information that you're passing. You're only passing the neighbor and its cost, and increase the frequency with which you get to that neighbor with that cost. Carry forward the information. I mean, you could, you don't want to retraverse everything again. Like ideally, if your lowest cost is the same, then you just increase the calculation from 0 to that node. You just increase the calculation from 0 to that node. And all the counts of the other ways is the same. Does that work? To push that information down. So like one option might be whenever you increase the frequency with which you see a node, then you have to retraverse it. Then you have to go through again where you push down that information in the second traversal. That doesn't seem to make sense. It's just way too slow. There's just way too many times you might need to update. But if you don't update, then how do you calculate? How do you know? Alright, so what if it was, so you always start with the low. Okay, so the heap here shouldn't work this way. The heap here should work as the lowest total cost. Yeah, because heaps do a sorting of the values that they're entering, and it should be sorting by the cost rather than the node, because the node doesn't really say much about the cost getting there, so it should be the other way around. Okay, so it should be sorting by the cost and then the node. But how does it differentiate between one cost and the next cost? Or one way of getting to a node and the next way of getting to the node with the same cost. Oof. Okay. Let's think about this. So we have our heap. Our heap is going to 0, having 0 cost to get to 0. That sets the low to 0 as being 0, and that sets one way to get there. So that's our starting way. And then from 0 we look at the neighbors and we add 2, 1, 7, 6, and 5, 4, the cost and the neighbor. And those will all be added because that cost is lower than the current cost of the neighbors, which would specifically be infinite. And then the heap will go through again and it'll pull out the 2, 1. And I'll say, yeah, this is better than the current way to get to 1, which is infinite. So there's one way to get here, which is 2. And then it'll add onto the heap 5, 3, and 5, 2. Because that will be the total cost to get to 3 from here, and the total cost to get to 2 from here. At that point, there will be 3 5s. in the heap will be 5, 2, 5, 3, and 5, 4. And it'll go through 5, 2 because it'll sort by low cost and by low node. And 5, 4 or 5, 2 will say that yes, this is the best way to get to 2, and then it'll look at the neighbors of 2, and the neighbors of 2 are the 1 and 5, and there's already a better way of getting to node 1, so let's ignore that, and it'll say getting to node 5, this is the best way, so it'll be 6, 5 added to the heap. The heap will be 5, 3, 5, 4, 6, 5, and 7, 6. So next it'll pull out the 5, 3. It'll ignore the 1. It'll say 5. It'll say 5, 3 is in the stack, or it will say that 5, 3 is also it'll say that 5, 3 is currently better. Like, it hasn't processed or updated the value for 5, 3 yet. So it should technically add 5, 3 to the stack or into the heap. Okay, there's a possibility there. Like, maybe keep track of what's in the heap in the increment. But then what if you later on find that after you reprocess the 5, 6, that you add another way of getting 5, 6. Okay, so when you do this, you add a second 5, 6 and a 2, 5, 8 and an 8, 6. Sorry. A second 6, 5. The cost is 6, the node is 5. So your stack at that point will be, alright, so stacks will be 0, 0, and then process that stack, or the heap will be 2, 1, 7, or 5, 4, and then 7, 6. And then from there it'll process the 2 of the node 1, which will add onto it 2 and 3, so it'll be cost is 5, node 2, cost is 5, node 3, cost is 5, node 4, and then cost is 7, node 6. Process node 2, it'll just add the node 5. Cost is, well, this is going to be 6 cost 5 node. That'll be after 5, 3, 5, 4, 6, 5, and 7, 6. And then we'll process the 5, 3. They'll say that there's another way to get to 6 that costs 5. So 5, 4, 6, 5, 6, 5, and 7, 6. Now technically heaps don't actually sort when you add stuff on there. It just keeps track of the lowest. But I'm just, for my understanding, it's going to be sorted. So how do you know? 6, 5, there's 2 of them. Two of them. I mean, you could keep track of all the could keep track of the particular path you went through. You keep track of the particular path that you went through. The issue is you're keeping track of a lot of paths. Like there's no, if the number of paths can be a huge number, 10 to 9 plus 7, there's no way that you want to store that many paths outside of a number, like a modular number. So what is current shortest path? Store the current shortest path to a particular thing. You're always processing the low. Right? You're always processing the low. And if you ever see something that is bigger to a node, interesting. Actually, by the time you reach a particular node, what if you increase the frequency? What if you increase the frequency when you see it, and when you process it, you set it in stone? So when you add a node and its low value to the heap, you reset the you actually do the processing for the low frequency. And then when you pull that from the heap, that's when you actually consider the count. So interesting. So when you've reached a particular node, there's no other way of getting to that node that's faster. If you pull a particular node from the heap, that means that there was absolutely no way to get there any faster. Because if there was, then the cost should have been already processed. Yeah. Okay. So when you pull a node from the heap, that is the low way. And that means that the heap, so should you add stuff to the heap? Should you add stuff to the heap? Okay. Yeah, okay. So I think I need to actually keep track of the number of ways to get here. So it'll be the heap is going to be the cost of the node, and the frequency. And you keep track of the frequency here. Frequency of this path. And I think the frequency of this path. So you get to a particular node with a certain frequency. So you go down this path, get to 6. There could be ties. Could be ties near heat right now. Oof. Okay. So get to node 0 with get to the cost of 0 to get to node 0 with frequency 1. And the frequency is the frequency some summation? Or is it some multiplication? The number of ways to get to this thing is like if there was is the sum of all the ways to get to this thing. There's multiple paths. So if you say that you added at the very start 7, 6, so 0, 0, 1, there's 2, 1, 1, 5, 4, 1, 7, 6, 1, and then the number of ways to get to 5 would be 5, 2, 1, 5, 3, 1, 5, 4, 1, and 7, 6 is still one way. Alright, and then when you process 5, 2, 5, 3 is still going to be 1, 5, 4 is still going to be 1, 6, 5. Or do you need to track the number of ways using the frequency counter? So for each neighbor that you see, so by the time you reach something, the frequency, the determination of the frequency to get to that thing should have been already fixed. Okay, so maybe do I just need to have a scene set? Or the scene if node in scene, then just skip this node. Do I even need to do this? Because every time you see a node, it has to be the shortest way, although there could be duplicates. Right? Yeah, there could be duplicates. Say, actually scene should just be false. Times I think this is a bad syntax error. This is, I think, syntax that. It's like that. Invalid syntax false. Indent error. Yeah. So yeah, you don't need to have the frequency. I think you just should use the low frequency when you see this item for the first time. So if you've already done this node, then if seen node is true, then continue. Otherwise, seen of this node is true, and the first time you see a node, that has to be the low, and the count of the number of ways currently to get to it is fixed. Okay. At that point. So first I'm seeing a node, number of ways to get to it is fixed. So at that point, the count is going to be is whatever the low frequency for this node is. And then for each neighbor, in the graph of this node, if the neighbor cost plus the cost is less than or equal to this cost, then we should do what we want to do here. We actually want to update. So slow time, not low cost. Oh gosh. Load time for this neighbor is equal to the neighbor cost plus cost. Load time for this neighbor is going to equal the number of ways to get the load time for this neighbor. The low frequency for this neighbor is going to be set to 1. And we're going to push that we need to explore this neighbor. Else, if the neighbor cost plus the cost is equal to the load time for this neighbor, then load time of this neighbor is not going to change, but the low frequency of this neighbor is going to increase by 1. And I guess since we already have the neighbor pushed, then we shouldn't need to add it again. Otherwise, the cost is bigger, so we ignore it. And we don't say that we've seen this neighbor until we actually hit this part. That's not quite right. That's not quite right. The low frequency for this neighbor should be set equal to the frequency that we currently have, or incremented by the frequency that we currently have. Yeah. However number of ways we have gone to the current node, if we're setting a new path to the neighbor node, then that's the same frequency. Okay. And this frequency should be modulo plus equals plus equal when do you do the modulo? When is the correct time to do this modulo? We do it here. Probably should do it here too. Low frequency of neighbor plus frequency modulo. And once we get to the last node, if the node is equal to n minus 1, then I think we just break. And then we say return return the low frequency for that last value. Okay, let's see if this works. If seen of node is true, how could it possibly be going out of bounds here? Zero, 1, 2, 3, 4, 5, 6, 7. What is the node that it could possibly be at here? Unless I create my array wrong, or my heap wrong. The node is equal to n minus 1, 26. Seen of node is true. Let's go and just print out the node. Should say what the node was before it crashed. Node 7. The cost and the node. Oh, I need to switch this. The cost, which is neighbor plus cost, common neighbor. Okay. I think that's fine. Okay, return 0. Interesting. Oh, did I never set the thing? The low time for this neighbor. Guess I never set it to 0 for 0. So maybe the load time of 0 should be load time for 0 should be 0 low frequency for 0 should be 1. No, low frequency for 0 should be 1. And then the first time it does the heap, it's going to pull that low frequency. Yeah. All right. Bam! Shazam. Nice. Very nice. Okay. Sweet. No big bugs. Alright, so how to explain this? So the summary of the solution is we keep, well, first is like you make a way to traverse graph, which is your map, which is your 2D array or your dictionary. But we use heap of tuples of low cost to node, comma node. In order to process the lowest path currently. Like heaps allow you to always quickly pop the lowest value in heap. And the reason why we do this is because we don't really want to, there's multiple ways of getting to any particular node, possibly, and we always wanted to just like do the shortest way. And if we do the shortest way at all times, then if we ever reach the node again, then we know that that's a longer way. And also, anytime we see a node, we know that pretty much we've gotten there in the shortest way possible, and the count of the number of ways that we've gotten there is optimal. So when we reach a node, the current count frequency of ways of getting there is optimal. Is like that is the best number of ways to get there. There's no like there's not another path that we haven't explored that to get there. That said, there's a bit of delay between when we add stuff to the heap and when we process stuff from the heap. So when we add stuff to the heap, when adding nodes to heap, we increase the frequency using a array to track. So we track using two arrays, a low frequency array and a low time array. The low time array tracks the shortest time to get to a particular node, and the low frequency tracks the frequency of the number of ways of getting to that node at that low time. So in the processing of each node in the heap, when we process it, we look at the neighbors, we compare the cost to get to that neighbor with the current low cost to get to the neighbor, and if it is better, then the frequency is going to be updated to get to that neighbor. If it's the same, then the frequency will be summed to get to that neighbor. But that's all added to the heap. And then when we pull stuff from the heap, that's when all the ways of getting to a particular node is finished. So when popping or pulling nodes from heap, the frequency is finalized. And then, when we reach the last node, we stop. All other paths or stuff in the heap is ignored. Because it's just longer ways or other costs that are higher than that. Time complexity for this thing should be what is the time complexity for this? Pretty much explores every path. Yeah, so in the worst case it explores every path because every path is like needed to actually get to the end in the shortest way, and there's no really, it's not like it's going backwards. It's preventing itself going backwards by not doing costs that are bigger. So this explores every node and path as it should, possibly as it can be part of the solution. So here it's going to be O of n plus m, where n is the number of nodes and m is the number of edges. And the space complexity for this is again a 2D array plus a couple other arrays. So 2D array for all nodes and edges is going to be O of n plus n as well. And then the array for the shortest stuff and whatnot, we've seen it. Those are, and if you O of n arrays, so overall this is O of n plus n. All right, and that's a wrap. Interesting. I probably should have gone this a little